Okay, we're going to continue on here. Chapter 12, kinetics we've been talking about here. So remember last time we got into kinetics, which is really the first chapter of this course. Also a little bit different than some of the other stuff we're going to talk about in this course. But kinetics does sort of deal with kind of how fast or slow a reaction will take place. Remember, as we also touched upon thermodynamics, which we'll talk a little bit more about later on in the semester, deals more with the idea of will a reaction take place. Kinetics, again, deals with how fast or slow that reaction will take place. We started talking about really one way we could kind of look at the kinetics of an experiment, and that is what is sometimes referred to as the rate expression. And really, for any sort of reaction that you have, you can write a rate expression for each of the reactants and products. Overall, again, the rate here would equal minus, as we talked about, because we would expect the reactants to be decreasing with time, the change in the concentration of A over the change in time. We also talked about an important aspect of it, which is we do want to take into account always the stoichiometry that's involved. So we can kind of do that by taking the coefficient and taking 1 over the coefficient to do that. So that takes care of both the sort of stoichiometry and the kinetics together. Again, the idea here with the negative is when we do the change in our concentration, because A is getting smaller with time, our final concentration will be smaller than our initial concentration. That will get us a negative, along with, obviously, as we talked about, this negative will turn our rate into a positive number, which again is typically what it should be. For our other guy there, we would also have a negative because it's a reactant, 1 over B, change in concentration of B over the change in time. When we get to the product side, we should expect it to be increasing with time, as we should be making products, obviously, at this point. That means we do not need the negative, but we still want to take 1 over the coefficient, again, to take into account the stoichiometry, change in the concentration of C over the change in time. The reason, again, we do not need the negative here is when we do this calculation, because our product should be increasing with time, our final concentration should be larger than our initial. So when we subtract it, we will get a positive number when we kind of do that. And again, that will give us our positive rate. Remember that you can basically relate the entire reaction together here. You could also just, as we did in a couple examples, pull out maybe what you're interested in. Again, if you're interested, say, in our first guy here, and maybe you're interested in our product. And in this problem, maybe you're given information about how A is changing. That would allow you to solve for the rate or the average rate of the reaction, which the nice relationship is that is the same rate that we would have over here. And that would allow you, again, to maybe solve for how C is changing with time as well. So it really is, you just know one piece of information about how somebody in that reaction is changing with time. You can basically relate it to everybody else in that reaction through this sort of rate expression. Remember as well that as I mentioned, the average rate is typically a positive number. But if you are solving, like we did in maybe a couple of examples there last time, if you are solving, for example, how, say, a reactant is changing with time, you will end up with a negative number again, because it should be decreasing with time. Or if you're solving for how a product is changing with time, you will end up with a positive number as well. So, kind of depending on what you're solving for, you may have a negative side, especially if it's a reactant, what you're solving for. If you're solving for the overall average rate, you should be positive. Or if you're solving for how a product is changing with time, it should be positive as well. Any questions on any of that stuff there we talked about? Okay. So we laid up right here at the rate law, and let's talk a little about the actual rate law, which is a little bit different in some senses of the rate expression. But the rate law does express the relationship of really the rate of the reaction to its concentrations to some type of order. So if we have this reaction, we could write this sort of generic rate law here. The rate is equal to K times the concentration of A to the X and B to the Y. So this is our rate of the reaction, which is typically a molarity per second. This is our rate constant that we also sort of saw last time as well. That is a relationship in this reaction that will give you really a constant value. Um, and sort of determine how fast or slow, for example, a reaction will take place. Again, typically the larger the rate constant, the faster it will happen. I kind of lower the rate constant, the slower. These are our concentrations. When we look at X and Y, these are what are referred to as orders. So X is the order for respect to A, and Y is the order with respect to B. We could actually calculate the overall order for the reaction by simply just adding those two orders together, and that will give us our overall order that's happening in this reaction. So you could think of sort of the orders, and by the way, pretty much the orders are always found experimentally, and really the rate law as well is typically found experimentally. So as we'll see shortly, you're typically given tables to help you sort of experimental tables to help you sort of solve for the orders and the rate law and so forth. But again, the X and the Y is again sort of again the proportion of those molecules that you need to sort of sustain a specific rate that's happening. So why is, say, a rate law sort of important to know, or what is sort of a practical application of a rate law? Well, first off, one important application of a rate law is it only involves reactants. Yeah. So pretty much as you can see here, it is all about reactants. There typically is in a normal rate law no products there, so it's only reactants. It's all about the reactants. How they're going to react is going to determine the rate of this particular reaction. Now, what is sort of, again, a sort of practical application of knowing the rate law? So let's just say, for example, we had a rate law where we had K and A, and typically you don't write the ones, but I'll write it here. A to the first order and B to the first order as well. And again, typically we don't write the ones. If we wanted the overall order here, for example, just to show you, just add those together. And in this example, this would be overall a second order reaction that's happening by simply just adding our orders together. So why or how can this rate law, for example, help you in a real life situation? Well, for example, if I say had a concentration of A that was say 2 molar, and I had a concentration of B that was say 2 molar. And if I put it into this rate law that I have, I essentially have the rate is equal to, and I'm just going to ignore K for now, since it's a constant number. It won't really make any difference. We'll have 2 and 2, which gives me an order of something like 4 molar seconds, right? So something like that. So let's just say that this rate, or you're trying to maybe do something with this reaction, and maybe you want to like slow it down. It's like maybe happening too fast. So for example, if I did it again, and what I decided to do was, for example, I will keep my A at 2 molar, and you know what, I'll cut my concentration of B in half to 1 molar. So if I run another experiment with this one and I do that and I put it in there, my rate would equal, again, I'm not going to worry too much about K in this case. This would give me 2 to the 1 and 1 to the 1, which would give me something like 2 molar seconds. So you can see that, you know, if I did this original reaction with those concentrations and I find that maybe it's too quick for me to take measurements or something like that, in this case, I could cut the concentration of B in half. And what happened to the rate when I cut it in half? The rate also cut in half, right? So by just simply cutting half of, not both reactants in this case. I could slow it down even further by cutting both reactants in half. But in this case, by just cutting B's concentration in half, I was able to slow down this reaction by half, right? And kind of slow it down. Maybe that would allow you to, for example, measure whatever you're looking for. Or the opposite is true as well. Maybe like you're doing an experiment and you're like there all day going, Jesus, thing's forever. It's never going to finish or never going to happen. So what happens if I decide I wanted to kind of speed it up? Again, I leave 2 molar for A, and this time maybe I double the original concentration of B. And if I put that in there, and again, ignoring K's sort of contribution, as it would be the same number in all these, we would have 2, and then we would have 4, and that would give me 8 molar seconds, for example. And we can see in this case, by doubling the concentration of B, my rate actually went up by half, right? So I was able to speed up the reaction. So knowing the rate law for a particular experiment can be really beneficial, as it allows you really to be able to, for example, play with concentrations. You could optimize the reaction that you're studying, for example, and have it run at sort of a time period, which allows you to do that. Again, when we do our kinetics experiment next week, maybe, they played with that. They found again that the reaction was too fast for students to get in there. So they had to look at the rate law and figure out, what can they adjust to maybe slow it down long enough for students to be able to actually take readings. Now, this is also dependent in this particular case, right? We would see the same sort of effect if we did the same sort of either cut or increase in the concentration of A, or like I said, you could even make it go a lot faster or a lot slower by playing with both concentrations, really, sort of adjusting both concentrations. Now, let's say I had a rate law of the rate is equal to K times A. And again, don't usually write the 1, but I will in this case. And we'll say B to the second order. In this case, the overall reaction would be third order if you add both of those orders together, the 2 and the 1. So now let's see what happens with our rate if we just started with the same concentrations we had in the first experiment, which is basically 2 for each of these guys. So if we put that in there, the rate is going to equal to K 2 and 2 squared, right? So that's going to give me basically 8 molar seconds, something like that for my rate. We can see the effect of having this concentration to the second order, even using the same concentrations we had previously. We're now starting out at a baseline of twice as fast as that first reaction was, where they were both first order. Now, again, if I wanted to slow it down, maybe I cut my B in half and I go with A is 2 molar, B is 1 molar, and I put it in there, and that would give me the rate is equal to, again, ignoring K, 2 times 1 squared is 2 molar seconds, for example. I cut B in half this time, right? What happened to my rate? Did it get cut in half? It didn't. It got cut even more, right? It got cut by a factor of 4, right? So because the order of B is second order, it has a greater effect, right, on the overall rate than, say, if you cut A in half, right? If I cut A in half, we would not see as big of a drop because obviously A is first order in this particular case. Same thing as well, if I wanted to speed it up and I threw A as 2 and B as 4 molar, that's going to give me 8 times 2 is 16 molar seconds, right? So here I, again, sped it up. That's bad math there. That's 32 if I did that math right there. It looks a little better, maybe. 4 squared is 16. 16 times 2 is 32 in that case. So here I did increase the concentration of B by doubling it. And we also see that, again, that the rate went up by a factor of 4 in this particular case. So it does depend on the reactant, depends on the order that it is as to how big of an effect, for example, it may or may not have. Again, if we didn't want our rate in the second example to sort of increase that much or decrease that much, Again, if we played with just A in this case, we would get a little bit milder of a increase or decrease depending on what we're doing. Any questions on that there? Now, what happens if I did have this rate law, which is, say, the rate is equal to K times A to the 1 and B to the 0, right? Something to the 0 power is what? It is 1, right? So this becomes 1 basically, right? So in this case, right, if I add my A, which is 2 molar, and my B, which is 2 molar, that would give me the rate is equal to K, again, 2 and 2 to the 0, which gives me a kind of 2 molar seconds rate, right? What happens if I increase the concentration of B to something crazy like 16 molar? Would it have an effect on the rate of this reaction? It would not, right? Because once you put that 16 in there to the 0 order, it's first, it's 1, right? So you could play in this particular reaction with B as much as you want. Is not going to have an effect on the overall rate of the reaction. Here you would be forced to obviously do something with A, as that's the only one that obviously would affect the overall rate of this particular reaction. Any questions on sort of the practical real life application of sort of a rate law there? Okay. So let's talk about how we can actually calculate this. So as I mentioned before, typically speaking, to calculate a rate law, it's all about experimental information. And typically speaking, you will be given a table of experimental information. And typically what you will be given is a table of reactants. And you'll be given like an initial rate, which is like molar seconds. And these are molarities. And typically speaking, you will be given a number of experimental trials, basically. And the idea here is you're going to try to figure out what each of these orders are to begin with. So you have the concentration here of each of these guys would be given to you. And again, you would have the initial rates of each of these guys given to you. Now, you could do it just looking at it, but most people maybe are not so great at that. So I recommend more of a math approach. And a math approach is this. You could just take the rate 2 over rate 1 is equal to K A to the X and B to the Y divided by K A to the X and B to the Y. Obviously here, if you had 3 reactants, you could use C to the Z or whatever it may be. So what does this mean, rate 2 and rate 1? It doesn't mean that you go to the table and just pick number 2 and number 1 that's listed in the table. You want to go to this table, and what you're looking for is a situation where you look at the molarities of, say, one of these guys. So we'll call this guy 2 molar. And you look at the sort of molarities of the other guy, and we'll go with like 2 and 4 molar, right? And you look at the rates, which I don't know, we'll go with 8 and we'll go with 8 and 4. Just make up some numbers. So what you're looking for is 2 entries where one of the concentrations basically remains the same and the other one varies. So you're looking for 2 entries where one stays the same, the other one varies. Again, the purpose of that is for you to basically end up with only one unknown at a time. You definitely don't want to solve for something that has multiple unknowns at a time. So if you do that, that's what you want to look for. Now, again, if you had a reaction where you had 3 reactants, you would look for 2 entries where 2 of the 3 stay the same and one of them varies in the same sort of thing. So what that means is you would take these 2 entries, for example, and you could look at experiments 2 and 1. And typically speaking, it doesn't really matter which experiment you put where, but if you want a little bit more whole numbers to sort of solve for, typically speaking, you want to roll with the one that has the larger rate up on top. You don't have to do that again. Otherwise, you'll get a little bit more whole numbers that way, a little bit easier to sort of maybe see the answer at the end. But if you want to do it the other way, you'll just get more decimal type numbers, but it works really the same. So what that means is in my example here, I'm going to take everything from the second experiment and put it up on top. So for me, that would be like that would be 8 if I read the number right, molar seconds equals K. And in this case, A's concentration is 2 to the X and B's concentration is 4 to the Y. Now I'm going to put everything from experiment number 1 on the bottom. That gives me 4 molar seconds, K, again, 2 to the X and 2 to the Y. Let's see how bad I did here. At this point, what we're going to do is a little bit of math. So if we divide these two guys, 8 divided by 4 is 2. Now, at this point, this is the rate constant and this is the rate constant, which means for this reaction, should that number be the same or different? The same, hence the name constant, right? So although we don't know what it is, we do know that they should be the same and they should cancel out. Now, we don't know what the order is here, for example, for A, but we do know for this reaction, it also should be the same number, which means that essentially these two guys are going to cancel out, which is why we want to make sure we choose one where they stay the same so that they completely cancel out. Now here, 4 divided by 2 is 2 to the Y in this case. And at this point, you could probably visually see with the big numbers there that Y is equal to 1 in this case. By the way, if you don't really have a pretty number or something like that, you can take the natural log of both sides. And when you do, that'll bring the Y down and then divide by the natural log to the other side. And you can do that if you don't really have pretty numbers. So you can just natural log both sides and divide it out to get you kind of a whole number. Now, once you do that and you figure out the order now, for example, with respect to, we did B in this case, you then would go back to the table. And in this case, you would want to, and I'll just make up some numbers here. We'll just go with, go with 4 molar here. You would want to go back to the table and now find 2 entries where B stays the same, which in this case, B is the same in those 2 entries and A varies, and you do the same type of calculation there for A and get both orders. Once you determine both orders, you then would have the completed rate law with the orders. You could use that then to solve for the value of the rate constant. Any questions on that there? Let's take a look at one with some real numbers here together and see what we really need to do. So here again is like I said before, a typical type of table of information that you're given. And once again, you're typically given the concentrations of both reactants or all reactants. If there's more than 2, a lot of times it is 2, but sometimes it could be 3. In this case, once again, we have 3 experiments. Sometimes it could be 4, 5, 6, 8, 9, 10 experiments, a bunch of experiments. It doesn't really matter. You just want to pick 2 of the same. So we'll start here with just a generic rate law, I'd like to call it, which is the rate is equal to K times the concentration of our reactant, which is F2, and I'm going to call that to the X, and our ClO2 to the Y. Remember again that the rate law is only about reactants, so no products involved. So at this point, I'm ready to try to figure out first off the orders here. So I'm going to go to my table and I can see just simply looking that if I go with number 1 and number 2, the concentration of F2 stays the same, while the concentration of ClO2 basically will vary. So we're going to start with that, which is experiments 1 and 2. Again, we could use our sort of mathematical approach, rate 2 over rate 1, RK A to the X, B to the Y, and RK A to the X and B to the Y here. Obviously, A and B represent basically these guys, right? So here we will put in our numbers, and in this case, if we do look at the rate here, it does look like experiment 2's rate is larger than experiment 1. So once again, I'm going to put that larger number up on top to try to get maybe a nicer whole number. So everything from experiment 2 in this case will go up on top, 4.8 times 10 to the minus 3 equals K 0.1 to the x and 0.04 to the y. Once again, all those numbers come from experiment 2 in the table. Obviously, you cannot mix a mass experiment, so you got to put everybody on the same experiment on the same line. We're now going to do the same thing here for experiment 1 and put all of our numbers in. 1.2 times 10 to the minus 3, RK 0.10 to the x, 0.01 to the y. So we're going to do our same math here, which is basically 4.8 divided by 1.2. So that is going to give me a 4. Once again, my rate constant should be the same for both, although I don't know what it is right now. Should be the same. My x in this case should be the same for both of these. Once again, don't know what it is right now, but they should allow it to cancel out completely. And once again, in this case, we get a 4 to the y. And in this case here, y would equal 1. Yeah. Any questions on that there? Now that I figured out the order with respect to the ClO2, I'm going to go back to my table. And now what I want to do is keep the ClO2 constant. So we had that one very last time. So this time we want to keep the ClO2 constant. And it looks like if we maybe go with experiment 1 and experiment 2, that will keep both of those guys constant in this case. So once again, I'm going to choose experiment 1 and 3. I'm going to choose the larger value for the rate to put on top, which in this case is experiment 3. So that's going to put me 2.4 times 10 to the minus 3 equals k times 0.2 to the x, 0.01 to the y. And again, that is everything from experiment 3. Once again, here we're going to go with everything from experiment 1 on the bottom. 1.2 times 10 to the minus 3, k, 0.1 to the x, 0.01 to the y. Once again, doing a little bit of math here, that's going to give me a 2. These guys are going to cancel. These guys will completely cancel. And now we will have a 2 to the x. X is equal to 1 in this case. By the way, it doesn't always equal 1, but happens to, obviously, in this example here. Any questions on where any of the numbers came from or anything like that? So this is really the first thing that you do want to kind of determine to help you figure out what's going on with this rate law. Now that we have it, we actually have the completed rate law that we could do, which is the rate is equal to K times F2 times ClO2. Once again, here we typically do not write the ones, so if there's nothing written on top, it's assumed to be first order for each of those. We could also figure out at this point the overall reaction is the overall order is basically 1 plus 1, which means overall this reaction is second order by again adding our orders together, basically. Yeah. Question on that? The last thing that you typically do at this point, once you have figured out the overall order, once you figure out the orders of each of these things, is we oftentimes also want to figure out what is the value of the rate constant for this reaction. So now that we get the orders, we could actually do that. By the way, you can't do that until you get the orders. So that is the order at which you should do it, which is get the orders first and then get the rate constant. So how do we get the rate constant? Well, now that we have the orders, we can simply take the rate law that we calculated and solve for K. So if I solve for K, that's going to give me the rate divided by F2 and ClO2. And again, that's basically just taking these guys and dividing it to the other side, right? Where do I get those numbers from? I could get those numbers from the table. So I could use experiment 1, I could use experiment 2, I could use experiment 3. It is a rate constant, which means no matter which experiment you grab, should give you the same number. So it doesn't matter which one you grab. You grab experiment 1, experiment 2, experiment 3. The only thing that you cannot do is mix and match. So you can't kind of like grab stuff from each one. You have to use it all. So I'm going to grab all the information from experiment 1 and put it in here. That means that my K will equal 1.2 times 10 to the minus 3 molar seconds divided by F2's concentration, 0.1 molar and 0.01 molar in this case. And if I do that, making sure you use your exponent button, 1.2 minus 3 divided by 0.1 divided by 0.01. That's going to give me a rate constant for this of 1.2. Now, the units for the rate constant is really important as well. So unit-wise, what happens is the molarity on top and one of the molarities on the bottom will cancel each other out, and that will leave you 1 over molar seconds as your units. Or sometimes people will do m to the minus 1 s to the minus 1, whichever way you want to do it. That is, by the way, as we will see, the very common units associated with a second order reaction overall. So as I might have mentioned earlier, and I'll mention again probably before we're done with this chapter, a lot of times you do need to know the overall order of the reaction. And in a lot of problems, they will not just come straight out and tell you it, but they will give you the value of the rate constant, and you can basically determine the order of the reaction by looking at the units of the rate constant. Any questions on that? Again, you should get that 1.2 value regardless of what experiment you put in there. They all should be the same. Now, in this case, our orders for these guys on the bottom were ones. If they were some other number like 2 or whatever it may be, you would obviously need to square the number when you get down to this part. If it was a second order or something like that. So you do have to take the orders into account when you're solving for obviously the rate constant. Any questions on those steps there? So as we see there, the rate laws are always determined experimentally. And the reaction order is usually, in terms of the rate law, always about reactants, really no products in a rate law. And the order is not related to the coefficient, although in some cases it will be the same number, but that's not how you get the order of a reactant. You have to actually use the experimental information to determine it. So as we can see in the case of ClO2, the coefficient was 2, but obviously the order here is first order. All right. All right. So the rate equation for this reaction of NO going to ozone is the rate is equal to KNO times O3. If the rate is 6.6 times 10 to the minus 5 molar seconds, when the concentration of those guys, what would be the rate constant? So take a moment and calculate the rate constant. Give us the rate laws. So we got our rate is equal to K, NO, and O3. And they gave us the rate, which is our 6.6 times 10 to the minus 5. Here we're going to solve for K. So we're just going to bring these guys obviously to the other side, which will give us our rate divided by NO and O3 in this case. So pop it in the numbers since they gave us all those numbers, 6.60 times 10 to the minus 5 molar seconds divided by our NO concentration of 1 times 10 to the minus 6 molar and our 3 times 10 to the minus 6 molar. And in this case, we will end up with about 2.20 times 10 to the minus 7. In terms of the units here, molarity and molarity will cancel, giving us 1 over molar seconds. And this would be a second order reaction, as those are the common units. And we know that from 1 and 1, telling us 1 plus 1 is second order overall in this reaction. So the units do match what the overall order should be in this case. Questions on that one there? All right, so why don't you try one here? Let's calculate the rate law, the orders, the value of the rate constant. So let's just do everything. So what is the completed rate law with the orders? What is the overall order of this reaction? And what is the value of the rate constant? Okay. All right. So based on this experimental information, see what you come up with. Okay, so let's take a look, see how you're doing. So again, we can start with kind of the generic rate law here, which should be the rate is equal to K. Remember, it is just our reactants involved here. So we'll call this guy to the X, and we'll call this guy here to the Y. And again, no products going on. Here, we want to look at our table, and we want to keep one of the concentration is constant, and I can see I could do that there by taking experiment 1 and 2, as that guy will stay constant, and obviously our I minus will vary. So looking at experiments 1 and 2 and putting our numbers in, here I am going to put actually experiment 1 up on top, as it has the larger rate value, which should give me a little bit more of a whole number. So that's going to be 2.2 times 10 to the minus 4 up on top. K, our 0.08 to the X, and our 0.034 to the Y here. And again, that is everything there on the first entry. Now we will then put everything here for our second entry, and that is 1.1 times 10 to the minus 4, our 0.08 to the X, and our 0.017 to the Y. My Y is sort of there. There's Y. Doing a little math here, that's going to give me a 2. These guys again should cancel. The X guys here will also cancel, as they should be the same value. And dividing out our other one there, that looks like a 2 to the Y. That means in this case, Y is equal to 1. Once again, you could take the natural log both sides and divide, but you really don't need to in this particular case. Any questions on that there? Now that we took care of I minus, we now want to keep that one constant and vary the other. So that looks like experiments 2 and 3 will actually achieve that for us here. So we'll look at then experiments 2 and 3 in this case. And here we're going to put experiment 3 up on top, as it does have a larger value for that. So that's going to go 4.4 times 10 to the minus 4 equals K 0.16 to the X, 0.17 to the Y. Once again, we're going to put experiment 2 here on the bottom. So we'll go with 1.1 times 10 to the minus 4, K, 0.08 to the X, and 0.17 to the Y. Doing our division here, that's going to give us a 4. The K's will cancel. These guys will completely cancel. And that's going to give us there a 2 to the X. And you can probably see X should equal 2 in this case, right? 2 squared is 4. Any questions on that one there? That means that our sort of completed rate law here would be the rate is equal to K times S2O22 minus, that one is squared, and I minus again to the first. That means overall order of this reaction is going to be 2 plus 1, which is third order overall. The last thing that we have to do now that we have the actual completed rate law with the orders is we can calculate the value of the rate constant. Once again, to calculate the value of the rate constant, you could choose any entry you want. You really don't have to do it for all of them, because they all should come out the same number, since it is a constant. So you just need to choose one. No mix and matching though. So again, here I will, just for the fun of it, we'll do number 2. I'll put number 2's into here. And if I did that, in this case, I get to solve for K. And I'm basically just going to take these guys and divide it to the other side. And that will give me K is equal to the rate divided by S2O82 minus squared and I minus here. So since I said I'll do number 2, that means up on top 1.1 times 10 to the minus 4 molar seconds divided by 0.08 molar squared and 0.17, I missed a 0 there, 0.017 molar, and that's a 1 there. Now, that's going to give me here, looks like 1.1 to the minus 4 divided by 0.08 squared. And divided by 0.017. Give me a, go with a 1 point. We'll go with 1.0 in this case. And that's going to be in terms of units here. Molarity up on top and molarity on the bottom will cancel. We still have molarity squared there on the bottom. 1 over molar squared seconds in this particular case. Any questions on that one there? Again, these units that we see for the rate constant are different than what we saw for second order. Just out of curiosity, those are 3 letters on the bottom, so that's like third order, right? And 1 over molar seconds is like 2 letters, so it's like second order, right? So sometimes you count the number of letters. I'll tell you the order of it. Any questions on that there? All right, let's try another one here. Why not? Let's go with this one. Same thing, rate law, orders, rate constant. Sort of our rate law here that we're looking to find, so our NO2, we'll call that to the X, or CO to the Y. Once again, we're going to look for, again, 2 entries that one stays constant, the other one varies. In this case, we have 4 experiments, so it does work the same. It just gives us a few more options. For example, obviously, experiment 1 and 2 will do that. You could also do 1 and 4, and you could even do 2 and 4 will also do it for you. So you have a few different options in this particular one. They all really should give you the same answer when it's all said and done. So it doesn't really matter which one you choose. So I'm just going to take the first 2 in this case, which is experiment 1 and 2. And again, I'm going to go with the larger rate up on top, which looks like it is experiment 2 in this case. So that's going to give me 0.0082 is equal to K times 0.2 to the X and 0.1 here to the Y. We're now going to put everything from experiment 1 on the bottom. So 0.0021 K, 0.12 and 0.1 to the Y. So now when we do a little division here, we might not get as pretty numbers. So we do get something like 3.90476. Why not write them all? Equals, and this side should cancel. This guy should completely cancel, and this should give me a 2 to the X. So you do have a couple options like I talked about before. You can take the natural log of both sides if you want. And if you do that, that'll give you 1.3621961 equals our natural log of 2. And that does bring the X down. You could then divide the natural log of 2 to both sides, which is 0.693, by the way, divided by the natural log of 2. And that will give you an X is equal to basically 1.97, which is fairly close to 2, basically, right? You could, the other option was go, that's probably pretty close to 4, and obviously 2x to the 4 is going to give you 2 as well. So you could probably do that, obviously if it's close. And again, this is based on experimental information, so sometimes you don't get pretty nice numbers all the time. So if it is close, you can do a little bit of rounding along the way to sort of figure it out. Any questions on that there? All right, so once we did that one, we're going to keep the CO constant. We already did, actually. We're going to keep the NO2 constant at this point. And that looks like you have less options, actually, in this case. You only have really one option, which is experiment 2 and 3 to do that. So experiment 2 and 3. Here, slightly larger, I guess. We'll go with that guy up on top, 0.0083 equals K 0.2 to the X and 0.2 to the Y. divided by experiment 2, 0.0082, k 0.2 to the x and 0.1 to the y. In this case, once again, if you do divide it out with the actual numbers there and just don't call it a 1, you do get like a 1.012195,122. Again, these guys cancel, and that gives you 2 to the y. Really, at this point, that is probably 1, right? So something to the 1 is y would have to equal 0 in this case. If you want to take the natural log of both sides, you could. And if you took the natural log of this number here, so if you decided to take the natural log instead, you would end up with 0.0121212 all the way across, equals the natural log of 2 to the y, natural log of 2 divided by the natural log of 2, and you will end up with 0.017, which is pretty close to 0 anyways. Yeah, so again, you could go either way that you want in that particular case. Any questions on that there? So again, this is a good example to show you. Again, it's based on experiments, so not always going to be the prettiest of numbers. I will say probably a lot of textbook problems might be nice, easy numbers, but sometimes they may not be. At this point, we now actually do have our rate law, which is our rate is equal to K and NO2 squared. And the CO is to the 0 power, which means you can just write the rate law like this, which is probably a good idea. Why would I not want to write the rate law like this? Why would I not want to write like that? That would imply the CO has what order? That implies it has 1. So if you want to write it in, it's fine, but in this case, you would need to put the 0, yeah? Otherwise, it would imply that it does have first order and stuff like that. So again, in this case, you can't just write the other guy R. You can write it, got to put the 0 in to imply that 0. That means in this particular reaction, right, the only reactant that really determines the rate of the reaction is which one? Which one is the only one that really has an effect on the rate of the reaction? It is the NO2 in this case, right? Again, with the CO being 0 order, you could do whatever you want to that. It's going to have really no effect on the overall rate of the reaction. So it's really the NO2 here that basically is what's determining the overall rate of the reaction. Once we have that, we could solve for K. We're going to choose one of these guys here, and we will solve for K, which is in this case the rate divided by NO2 squared. Popping the numbers in there, that's going to give me 0.0021 molar seconds divided by my 0.1 molar squared. And that will give me 0.0021 divided by 0.1 squared. Going to give us, looks like a 0.21 units here. Molarity on top. One of those guys on the bottom will cancel. 1 over molar seconds in this particular case. Any questions on that one there? Yeah.
Does it like CO how it tends to like 1? Would it still have 1 molarity? So we're gonna
Say it again. For CO has 0 order, and what are you asking now? With CO, yeah, if you actually, for example, are you asking if you put it in like with that when you solve for K? Is that what you're asking? Yeah, so it would be in this case, it would be 0.1 to the 0 order, which should still be 1. It wouldn't, because it would turn out to 1. So overall, this reaction is second order. So those are the units associated with it. So unit wise, if that turns to kind of 1, the unit kind of goes away with it in a sense. So, yeah. Other questions? All right, one last one here to make sure.